It's Jason again, and today we're going to be talking about some more Siemens technology that you might be running into as you explore your PLC world. Today we're going to be talking about data records. I know, it's super exciting, and honestly, a lot of people don't run into this in your PLC, so this is probably one of those deep dive, a little bit more advanced topics. But once you get into them, it opens up a whole new world of possibilities. What is a data record? A data record is a piece of communication that is available for an I/O device. Normally, when we think about I/O, we think about what's called cyclic communication. Cyclic communication happens ever so often, however, how often is determined by the actual PLC itself. In the Siemens world, that'll happen every scan, and all the I/O will get updated and made available to the PLC. Let's take a look really quick at what that looks like in the PLC. So I have this agriculture system that has quite a few different nodes and different I/O. As you can see here, it's a lot. But what we want to look at is the difference between, like we said, a data record, cyclic communication, and acyclic communication. So everyone is pretty familiar with what cyclic communication looks like. So on this, we can go and click on a device, then go to I/O tags, and we see all these tags here. And they have an input address. So in this case, we have input 38.0 in this Siemens PLC would be made available for use in the PLC program. So if you just had an input, you could say input I38.0, or you could type in the tag RR-C-receiving, etc., and that would be available. And it gets updated every cycle. So when you hear people talk about cycle times, that's what this is talking about. The standard cyclic cycle time for a PLC. In Siemens world, that is determined by a block called OB1, so Organizational Block 1. And Organizational Block 1 is basically everything that you want to just run as fast as it can, and that's kind of the main PLC loop. A lot of programmers, when they first start programming with Siemens, they just put everything into OB1 and it works fine. That's traditionally how PLCs used to be, and there might be a little bit better way to organize things if you start using Siemens a lot more. Even in Allen Bradley world and other processors, there are different ways to use things like subroutines and add-on instructions in order to organize your code so you don't have just a bunch of logic sitting in your main subroutine. Cyclic communication is determined by the I/O. Anything that comes up that has an input and output address is going to be cyclic communication. Now, what's the difference between what we're talking about today? There's this kind of secret world of I/O on some devices that are available by using what's called a data record read. I've particularly picked this device here because it is a Siemens 3RK hybrid motor starter. It has all of the tags available that you see here, but it also has a bunch of data records with a lot more data on the back end that is available if you use the correct functions. When you first start using data records, you have to understand that the way that you get access to these is by acyclically calling a function. Now in our case, we want to access and update this data as fast as possible, so we're running it in OB1. However, that may not be the best way because these data record reads do take a considerable amount of time. In our example, this whole plant was running on around a 3 millisecond cycle time. When I implemented all of these read record functions in order to pull all of this data, it almost doubled that standard cycle time to about a little under 6 milliseconds. That's still incredibly fast for almost 150 devices. But if that 3 millisecond increase could cause some sort of issue, you would definitely want to consider maybe putting these block updates in what's called a cyclic interrupt block, such as OB30. OB30, you can choose how often you run that code. By default, it's 100 milliseconds, but you can set that up to a few seconds. Let's talk a little bit about how we get access to this information. For this, again, I said that this was a 3RK hybrid motor starter. So let's take and look at the manual for this device. Here's what I'm talking about. It's an ET200SP hybrid motor starter, 3RK1308. These devices are pretty stinking cool because they take the replacement of a MSP and contactor or a NEMA motor starter and put them into an extremely compact form that you can put into an ET200SP remote I/O rack. I use them almost exclusively in mine just because of the sheer amount of diagnostic data that is made available to you. If you're using a Siemens processor, you can link this diagnostic data directly to such as a comfort panel HMI and pull out wealth of information when these things have problems. Even if you don't, you can use the data record read functionality to be able to pull this stuff. So where is this information held? Let's take a look here. In this manual, you'll see a ton of information. I've already pulled up the section about data sets. And so we look here and it mentions at the very beginning that you can write and read these data sets using these functions write record and read record. And we're definitely going to come back to the read record one because that's what this video is about. All the data that is available is in all of these different things. So if you want to pull up this manual, feel free to do so and look at everything that's available. A little ways that this is organized is you have data set 69 and then data set 72, and each of these entries will give further information about the different data in the data set. So which data sets are we wanting to use? Well, that's up to us. What are we wanting to look at? In our case, we are creating a data acquisition block in order to look at all of the currents and fault status of all of these hybrid motor starters in this plant. What we're wanting is trip data and current data. So let's see if we can find those in these data records. I will say, as we scroll through here, there's a lot of information, and sometimes some data is actually duplicated. So it all depends on how you want to access it, how you want to organize it. We are actually going to be using data set number 92, and we'll look at another one here in a second because data set 92 has a lot of information about tripping that we want available. So group fault, thermal motor overload, overload tripping, asymmetry, so like ground faulting, upper limit violation, so short circuit, current lower limit violation, so if it open circuit, so if you burn up or open up a contact, residual current tripping, so if for some reason you have some sort of short circuit and then there's residual current left in the motor after it's been turned off, so the motor's still turning, it'll trip. All sorts of stuff available here. And so we can even see here in byte 6 bit 7 that we have electronic supply voltage too low. So it can even tell that the power supply has been dropped out, all available in this data record. And again, that's data set 92. We're going to keep scrolling down because I've highlighted another one that we will be using, which is data set 94. That data set 92 didn't have anything about the actual current reading, and that's what we're wanting to use. So dataset 92 didn't have any information about the actual current of the motor. All of that information is in the red measured values section, or more easily said, dataset 94. So here we're looking at this, and we see that each individual phase current is called out, and make note here, we have a range of value of 0 to almost 800%, but the increment is in 3 1/8%. So the resolution of this current value here is only 3%. So keep that in mind. If you're seeing fluctuations inside of 3%, this current detection scheme is not going to pick it up. So let's take a look now in our program to see how we're actually using this. If you remember what I said a moment ago, we are creating a data acquisition block that pulls in a bunch of information and conditions it into a UDT, or in PLC, or in Siemens world, a PLC data type that we have specially designed for our ignition control system to be able to pull remotely into our server. All this block is doing is collecting a bunch of data from the system every time it's run and packaging it into a form factor that we've determined previously. You'll notice a couple things about this function. You see a lot of these pound or hashtags in all of these names. That means that we are inside of a function block. And there's a little bit of nuance in working with function blocks that a lot of users aren't quite aware of. But just know that a function block creates its own data and own tag inside a block so that anything inside that block always has access to it. For example, the read record block that is available that we are using is a function block. It just so happens we have put that function block into our own custom function block called AgDataAct_Starter. I'll go into a lot more detail about function blocks in general, but don't let the hashtags throw you off on this. Let's talk now a little bit about how to use the read record block, since now we know what records we actually want to use. Remember, we are calling this code essentially as fast as possible. We put it in OB1. We don't have to worry about how often this is actually getting updated. Let's talk about the read record block. The first thing is, if you want to use this block, you need to know where to find it. If you don't know that it is in the distributed IO menu in the extended functions tab of your instructions, you can always go up to the top, type in RDREC, and hit enter, and it will find any block that matches that description. Now, how did we know what block you actually needed? Well, you're watching this video and it has it in the title. But if not, it was in that manual on that first page if you want to go back and watch it again. So let's look at the inputs and the outputs of this read record block now that we know which record we want to actually use. It is fairly simple, but some of them might not make sense at first. We have an enable, a request, an ID, index, memory length, and record. The request, anytime it is true, it will initiate an acyclic communication to the IO device and pull the data record according to your inputs. The ID input is the actual ID of the device that we are wanting. If you notice here, we have a hashtag starter hardware ID. Let me explain what this is. Normally, this is just going to be a number, but inside a function block, it has its own variable. Anytime you see the pound sign, you know that it's going to be up in what's called our block interface. So let's open up our block interface to see where that is actually coming from. The very first input is starter hardware ID. And if you notice, it's hardware any. If you're not familiar with what a hardware ID is on Siemens PLCs, this might not make sense at first. But let's go back really quick and look at our hardware of a starter block. Go into our receiving and pull up the properties. Let's take a moment to pull up this hardware device and look at what this hardware ID actually is. The hardware ID can be found under Device View in our Device and Networks by clicking on the device and going to System Constants. And the hardware ID is just simply a 524. Now, in our function, wherever we call our block DataAct_Starter, we would have to input in this hardware ID to the input of that block, just like we would this read record block that we're talking about now. Again, more on function blocks if that's confusing, but that hardware ID is found in our Device and Networks, and it's this 524. There's two ways that you can actually input this. You can actually input just a 524. You can drag this tag into somewhere that it's used, or you can actually go through and start typing in the device, and it will pull up any system tag that is available that would match the input type. Now, I'm going to hit escape so that we don't overdo something that's actually working, but that's how you would do this. So the hardware ID is a simple number that's associated in the hardware configuration of the Siemens PLC. The index is the actual data record. If you remember, we want to use data records 92 and 94. So for the first read, we're going to be using data record 94. So that's index. Memory length is simply how many bytes we want to actually pull. This does not have to pull the whole data record. And if you are not going to use all of the data, I would suggest optimizing your pull or optimizing the read record so that it is not pulling more data than absolutely necessary. So let's look quickly back at the data record itself for 92. 92 has a lot more than 7 bytes. We only want to use up to this 6.7. There is absolutely 7, 8, 9, 10 through 11, 12 through 13. So data record 92 looks like it has 54 bytes in it. So we could be pulling up to 54 bytes, but we don't want to do that because all of this other stuff isn't even relevant, or for what we are using it for, cyclic data acquisition, we don't want a lot of this data. So we only pull 7 bytes. That is why the M length is 7. Finally, the last input is the record input. And this is just a place for us to store the data that is pulled out of the record. So when the device responds back to us, where do we want to put that data? Well, in this case, we have set up in our block interface an area called trip record. And as you can see, we just set it up as a simple array of 7 bytes because we're pulling 7 bytes using the read function. Now, we could go through and actually name each individual one of these bytes and break it down into the bit level using a couple of little tricks, but we don't really need that because we can directly reference a bit from a byte. We just want to look at the bits that we want that are called out in that document that we were looking at before and just use them. A couple of notes that I will say: you want to always check just to make sure that it is valid, because if there's not a change, then you don't want to update your outputs. I have had to go through, and because this is in a function block, I wanted to make sure that my values would not be changing in between cycles. That is why you see a little bit of extra data here. Looking at the outputs of the read record, you have a valid, an error signal, a status, and a link. As you could tell, most of these you don't need to use. As I said before, I'm triggering off of the valid bit in order to record the actual data and update my data. One thing to note about this read record block is that the PLC will actually skip ahead, and once this block starts working, it will come back later. So this block, if the I/O device does not communicate within one cycle, this block may not update every cycle. And so it could be that the data is coming on and off. That's why you always have to go through and look and see if the data is valid. If the data is not valid, then that means that the data hasn't been updated and it's still waiting on that cycle. So just to reiterate a little bit, my second read record is almost exactly the same. In it, I use the same scheme. I keep my hardware always on. I'm using the same hardware ID because I'm communicating to the same device. I'm just trying to pull a different record. I'm using the same hardware ID, different record, and because I'm only wanting 3 bytes of data that hold the current values, I'm only using 3 bytes. I'm storing those in a location that I've created in my data block called current records, and doing the same thing and checking on valid before I update the outputs. One thing to note specifically about these current values, because they are the individual phase currents, I'm wanting to average their values together in order to get some sort of average signal, because they will vary slightly. And that is what this FC6 function block is. It takes in a current record, which consists of 3 bytes, which I know is 3 individual phase currents from a 3RK200 hybrid motor starter, and then gives me a solid real output. If you notice, this is in real percent. So I'm creating a real value in this function block out of 3 individual phase currents and averaging them and doing a little bit of work that way, just so that my data going back to my ignition system is a little bit nicer. Now, I don't have any use for the write record functionality in this program, but the write record is very similar in as much as it takes in a hardware ID, it has a record location, and then a length. Then it has a memory location of the data that you're wanting to write into the device. Same thing with the write record. It is acyclic, and so it may take multiple cycles for it to actually execute. Don't worry about leaving the request input on. It will keep up with the fact that there is a current acyclic communication request for that device and not get backed up. The PLC handles all of that in the back. Now that you understand how to read data records from an I/O device, this opens up a whole new world. Once you have your device into your hardware config, it gets immediately assigned a hardware ID, and all you need is that hardware ID and your manual telling you the data records in order to access those data. Lastly, let's take a look at an example of just that fact. I have mostly Siemens hardware in this project, except for an IFM IO-Link. Now, it has a hardware ID just the same as any other device. And as you can see here, each individual device on that IO-Link master has its own hardware ID as well. Now that means if you're using an IO-Link device, you use the hardware ID of the individual device, not the hardware ID of the gateway itself, unless you were trying to access diagnostic data from the gateway. So with that, you pretty much know all you need to know in order to get started bringing in record data from I/O devices. Those devices can be anything from radioactive density gauges to RFID sensors out in the field. And all of this data is available simply by using the read record functionality. That's it for today, and I hope this video has been helpful to you. If it has been, hit that like button and subscribe. I hope to see you in the next video.